Hello students, welcome to Unit 6 Notes, Section 8.1. I'm going to do the warm-up today because it should be pretty quick. So square the lengths of the sides of each triangle. What do you notice? Let's see, 3 squared, 3 squared is 9, 4 squared is 16, and 5 squared is 25. We have, for this one, we have 5 squared is 25, 12 squared is 144, and 13 squared is 169. For this problem, 6 squared, 8 squared, and 10 squared, which is 36, 64, and 100. Probably the most difficult one here. We're going to do 4 squared is 16, 4 squared is 16, and 4 square root of 2 squared. Let's rewrite that one. Let's rewrite it as 4 square root of 2 times 4 square root of 2. Remember, things on the outside stay on the outside, things on the inside stay on the inside. So they'll multiply. So we will get, in this case, we will get 16 square roots of 4. Because 4 times 4 is 16, and 2 times 2 is 4. And 16 square roots of 4, well, that's the same as saying 16 times 2. Oops, I used the wrong color for these. Let's see. And so 16 times 2 is 32 because the square root of 4 is 16. So we get, let's take a look at these. What do we notice about all of these scenarios? Well, I don't know, how do 9, 16, and 25 relate? How do 36, 64, 100 relate? How do 25, 144, and 169 relate? How do 16, here I'm going to, yeah, so 4 square roots of 2 squared. And how does 16, 16, and 32 line up here? Well, maybe you might have noticed that 9 plus 16, that 9 plus 16 is 25. That 36 plus 64 is 100. That 144 and 25 is 169. And that 16 and 16 is 32. So added together, they equal the square of the third side. So that brings us to our lesson today, which is the Pythagorean theorem and its converse. So the Pythagorean theorem, some of you might have done this in 8th grade or 9th grade, Algebra 1. We're going to not only use the Pythagorean theorem today, though, we're going to work with numbers that won't be perfect squares. So we'll have to simplify them, simplest radical form. And we're also going to use the converse of the Pythagorean theorem. So there's a couple skills here today. It's not just the Pythagorean theorem, but it's also its converse. The well-known the well-known triangle relationship called the Pythagorean theorem is named for Pythagoras, a Greek mathematician who lived in the 6th century BC. We now know that the Babylonians, Egyptians, and Chinese were aware of this relationship way, way, way before the discovery by Pythagoras. It just wasn't written down or published. In its publishment, Pythagoras was probably, well, the Pythagoreans, not only the teacher, the Greek mathematician, but also their students wrote it down, and it became wide known and widespread. But here's the Pythagorean theorem. What I don't like to do is I don't like to leave it in this form. I like to leave it in this form. L squared plus L squared equals h squared. And the reason why I don't like a, b, and c is because what if a were to be here and c were to be here? And so now it's not a squared plus b squared equals c squared. It would be b squared plus c squared equals a squared. And we get too finicky. Let's not focus in on the letters, but simply let's focus in on legs of the triangle, which are these two, and the hypotenuse, which is this one. This one's always the hypotenuse because it's always opposite the right angle. So what I'm going to do is erase that, and I'm just going to list that this right here is the hypotenuse. And because that's the hypotenuse, these are the legs. So we have two legs and a hypotenuse, meaning that leg squared plus leg squared equals hypotenuse squared. You can put these in any order you want over on the left-hand side here. You can also rewrite it where h squared equals l squared plus l squared. So that's also, you can flip the sides as long as both l's go to the other side and the h goes to the left. Yeah, so those are your legs, your hypotenuse. Again, it follows this pattern: 3 squared plus 4 squared equals 5 squared. 6 squared plus 8 squared equals 10 squared. 5 squared plus 12 squared equals 13 squared. And 4 squared plus 4 squared equals 4 square roots of 2 squared. Quantity squared, the whole thing. Okay. Pythagorean triples are really cool. So Pythagorean triple is a set of non-zero whole numbers, a, b, and c, that satisfy the equation leg squared plus leg squared equals hypotenuse squared. Here are some common Pythagorean triples: 3, 4, 5. If you ever see 3 and 4, you know a 5 is coming if it's talking about the hypotenuse. 5, 12, and 13. 8, 15, and 17, and 7, 24, and 25. Those are some of the common ones. What's really cool is you can take any one of these, and they all work. So let's take a look at this one. 3 squared plus 4 squared equals 5 squared, right? So 9 plus 16 equals 25. So 25 equals 25. That is true. And what I can do is I can actually, I'll move this down a little bit. Let me put the proof off to the side right there. Well, here, let me prove a second one just to show you. I'm not going to prove all of them, but there's no need to prove all of them. Whoops. Huh, where's my favorites? Oh, there we go. Okay, here's another one. I'll do 5, 12, and 13. So 5 and 12 squared equals 13 squared. So 25 plus 144 equals 169. And so 169 does equal 169. I'll put these proofs off to the side here. Okay, what's cool about these though is you can actually you can take it and multiply everything by, let's say, 10, and you'll get 30, 40, and 50, and this still is a Pythagorean triple. You could multiply this one by 3 if you want to. You get 15, 36, and 39, and that also will work. You can magnify them as long as you multiply all three quantities by the same number. Okay, multiply this one by 2 if you want. Multiply this by 2, you get 16, 30, and 34. That's a Pythagorean triple as well. So one of the questions I'm going to ask you is, are these a Pythagorean triple? And multiply this one, let's say, by 4. So you get 28, 96 and 100. And here's how you know that they are a Pythagorean triple. Are they all whole numbers? Okay, that's one of the checks. Are they all whole numbers? You don't want a decimal, you don't want a radical, you don't want a fraction. And does legs squared plus legs squared equals hypotenuse squared? So does two of the lower ones square, does the sum of the lower one squared equal the greater one squared? So the sum of the squares of the lesser two is equal to the square of the greatest. Okay. So if they ask you, like, let's say they ask you, what color haven't I used yet? I used pretty much all of them, huh? Use that one, that one, that one. Okay. So let's say they ask, is 4, 5, 6 a Pythagorean triple? And so what you're going to do is do 4 squared plus 5 squared equals 6 squared. And so 16 plus 25 equals 36. 41 equals 36. That is not true. So the answer here is no. So it has all whole numbers. That's awesome. But you still have to check to see if they are a Pythagorean triple. All right, the converse of the Pythagorean theorem. So if the square of the length of one side of a triangle is equal to the sum of the squares of the lengths of the other two sides, then the triangle is a right triangle. That's exactly what we just determined here. To be a Pythagorean triple, it has to be a right triangle, which we proved it wasn't. Okay, and then here's another one. If the square of the length of the longest side of a triangle is greater than the sum of the squares of the lengths of the other two sides, the triangle is obtuse. Take a look here. If c squared is equal to a squared plus b squared, we have a right triangle. If c squared is greater than a squared plus b squared, look at how c squared, look at how it gets larger. What it does is it takes this triangle and it opens it larger. The longer that the hypotenuse is, the greater of an angle this becomes, making this an obtuse angle. Versus, it's an acute triangle when c squared is lesser than a squared plus b squared. So flip these around, put your hypotenuse here. So let me rewrite all three of them. Let me rewrite them right here. If h squared is equal to leg squared plus leg squared, we have a right triangle. If h squared is greater than leg squared plus leg squared, we have an obtuse triangle. And if h squared is lesser than leg squared plus leg squared, we have an acute triangle. So those three things you need to know. Why is this acute? Well, all three angles are acute. Why is this one obtuse? Well, two are acute, but that one obtuse angle makes it obtuse. Same thing in a right triangle. It has two acute angles, except one of them is a right angle. So we describe it as that, as it's as a one that's not common, unless all three are common. Okay. Pythagorean triples. Find the length of the hypotenuse. Do the lengths of the sides form a Pythagorean triple? First off, we do have a right triangle. So for it to be a Pythagorean triple, is it a right triangle? The answer is yes. So the second thing we have to do is do 20 squared plus 21 squared equals h squared, because we are going to test to see, we are going to solve for leg squared plus leg squared equals hypotenuse squared. We're going to solve for the hypotenuse. And if that is a whole number, if this is a whole number, right, because we already have a right triangle, that's our one check. But we want to make sure that this is a whole number. So we have 400 plus 441. Let's see. I have a separate calculator, so I'll do some work there so I don't do too much going back and forth. But I will show you how to use a calculator. So take a look at this. We do have a calculator. I like to use desmos.com. And we have everything right here. You don't need projector mode on. I'm just trying to make it a little bit larger for you to see. In this case, we're able to type in 20 squared. Notice this button right here is squared. We can actually type in plus 21 squared. And so we get 841, which is exactly what 400 plus 441 is. That's not why I'm on the calculator. What I'm trying to show you now is whether or not 841 is a perfect square. So let's check that out. Notice this key. I'm gonna, whoops. It won't let me highlight like I did before for this other one. But anyway, we're going to type in the square root of 841, and we notice that that is actually a perfect square. It's the number 29. So we are going to go back. We're going to evaluate this. We'll say 841 equals h squared. We're going to find the square root of both sides. So 29 equals h. Well, plus or minus 29 because the square root of 841. However, we can only use the positive value because side lengths are positive. So h equals 29. And therefore, triangle ABC is a Pythagorean triple. Because it is a right triangle and has, what did they describe it as? Non-zero whole number side lengths. Whole number, that's important. It can't be a square root, whole number, or a decimal. Okay. I'm not going to write that for each one of these. I'm just going to, we'll just say yes or no. It's a Pythagorean triple, but I just want you to have that information there. So next one, a triangle has a hypotenuse length of 25 and a length of 10. Find the length of the other. So it's a right, so the question is it a right triangle? And it says it is. So that's good. That's half the battle. That triangle doesn't look like a triangle. Okay. It's a right triangle. And so now we need to find the other length. So we have 25 and 10, but 25 is the hypotenuse. So we're going to do leg squared plus leg squared equals hypotenuse squared. And we know one of the legs is 10. So I'll say 10 squared plus leg squared equals, the hypotenuse is 25 squared. So we get 100 plus leg squared equals 625. And I'll take away 100. So leg squared equals 525. Now we can bring up our Desmos, see if the square root of 525, ooh, it is not a perfect square. Okay, but what I can do is I can simplify it, right? So 525, I think it's divisible by 5. And then is 105 divisible by 5, right? So I'm going to look for factors here, which I think it is, 21. So why don't I try to take 525 and divide it by 25 instead, and I get 21. So that's exactly what I'm going to do here. I'm going to write it as leg squared equals 525. I'm going to find the square root of leg squared, square root of 525. So leg is equal to the square root of 525, which I found to be a perfect square in there of 25. So I got what, 25 and 21? So I'm just breaking it down a little bit here. And I'm going to get rid of that and say leg is equal to 5 square root of 21. The square root of 25 is 5. Don't leave the radical sign. Some students leave this radical. They say, oh, the square root of 25 is the square root of 5. No, it's the square root of 25 becomes 5, and that's it. So we have 5 square roots of 21. And so in this case, the answer is no. Did it give us a name? No. This triangle, I'll write it out. This triangle is not a Pythagorean triple because it has an irrational, which means non-rational. That's what the radical does. It's irrational. It goes on forever. It's an irrational side length. And you know what? I really should say this right triangle. Because it is a right triangle. It just is, it has an irrational side length. All right. Here's when we're just finding the value of x. So we will do leg squared plus leg squared equals hypotenuse squared. And I'm given 8 and x. So I'll do 8 squared plus x squared equals 20 squared. And I get 64 plus x squared equals 400. Take away 64. So x squared equals 334. Is it 3? No, 336. Yeah, 336. Sorry. Okay. So 20 squared, which is 400. So 400, let's get rid of one of these. 400 minus 64 is 336, which I have. And now I'm going to find the square root of 336, which is irrational. And so I know it's not going to be a perfect square, but what I can do is I can start to look for factors of 336. So I'm gonna go bold and say 36. No, that doesn't work. How about 2? Okay. How about 4? All right. 4. What about 16? Because that's the next perfect square. 16 and 21. 21 is 7 times 3. So I know that that is as low as that's going to get. So I'll do 336, which is 16 and 21. Whoops. So we have x squared equals 336. We all know what's coming now. Boom, the square root. So x equals the square root of 336. x equals, and what I like doing on Desmos, because you don't have to rewrite it 100 times. You're just gonna, you can just, do your perfect squares divided by 1, 4, 9, 16. Okay, you get to just keep changing the value and seeing what works, which in this case is 16. All right, so we're going to get the square root of 16 times the square root of 21, because 16 times 21 is 336. And so now x equals 4 square roots of 21. We are done. All right, that's it. The hypotenuse of a right triangle has a length of 12. One leg has a length of 6. Find the length of the other leg. So the other leg, 12, and is the hypotenuse. We have a leg. So I'm going to do leg squared plus leg squared equals hypotenuse squared. 6 squared plus x squared equals 12 squared. 36 plus x squared equals 144. Take away 36. X squared equals 108. I'm thinking this is not a perfect square. So I'm going to have x equals the square root of 108. And so x is equal to, let's break 108 down. Right, you can check it. Square root of 108, you see it's not a perfect square. What we can do is 108 divided by 4. Okay, that's my lowest perfect square besides 1. I get 27. Now take a look at 27. 27 is 9 times 3. 9, 18, 27. Yep. So I can go more than 4. I can definitely go more than 4. What's the next one? 9. 12 is still 4 times 3, so I can keep going. 16. 25. 36. Oops. 25 won't work. 36 and 3. 36 works. That's because I knew 9 and 4 are 36. They both had a factor of 9 and 4 and with the 3. So I'm going to do 36. 36 times 3. And that will give me x equals 6 square roots of 3. Again, it's not the square root of 6. Don't double square root it. 6 square roots. So leave your answer in simplest radical form. The leg is, and I'll call it the leg here. The leg is equal to 6 square roots of 3. Actually, I'll leave it x, and then I'll rewrite it as an L. Okay, and it's in simplest radical form. So now the next one, here's a real world example. You have 2 docks, and the Parks Department rents paddle boats at docks near each entrance to the park. To nearest meter, how far is it to paddle from one dock to the other? So how far is it to paddle from one dock to the other? And this is just, larger numbers, but that's okay. 250 and 350. 250 and 350. So I'm going to do leg squared plus leg squared equals hypotenuse squared. 250 squared, because we're looking for the hypotenuse. 350 squared equals h squared. Okay. I'm going to do 250 squared, 350 squared, and add them together. So 250 squared plus 350 squared. I'm going to write out all my work. So we get 62.5. 62.5. And then the other one was 125.5. wait, 125.5, 122.5, my apologies, 122.5. And that's equal to h squared. And that together was 185,000. So 185,000 equals h squared. Okay. To the nearest meter, how far is it to paddle from one dock to the other? Why would we use meters? Why wouldn't we put it in simplest radical form and leave it like that? Well, no one says, it's 100 square roots of 2 meters, right, to get from one side to the other. Because it's just not really a relative amount. You would, instead of saying the square 100 times the square root of 2, you would actually just do that algebra out. So what we're going to do here for this one, we are going to do 185,000, and we're going to find the square root of that. And we'll get an approximate value for h. 185,000 square root of 185,000, and that's about 430.11. So say 430. So h is this to the nearest meter, so 430. Okay, the docks are about 100. And let's actually move this around a little bit because we should, it's a, oops. Normally we would answer that in a sentence. And so I'm going to actually answer that in a sentence. The docks are about, oops, 430 meters apart. And that's my final answer in a sentence. Okay. How far is it to paddle from one dock to the other? The docks are about 130 meters apart. That's how much it would be to paddle. Makes sense. 25, 250, 350, 430. It fits the pattern there. It has to be a little bit larger, but not too much larger. All right. When you want to know how far to paddle a boat, why is an approximate answer? And I've already answered this one, more useful than simplest radical form. It makes more sense to give an answer, to give a real world answer as an exact measure, as an approximate measure. An approximate measure or length rather than an exact length in simplest radical form. Because it's more understandable. intangible, like tangible meaning tangible, ABLE, IBLE, hold on one sec, ABLE, no, IBL, I was right the first time, tangible. And tangible, so tangible meaning like the perception, um, like perception by touch, meaning that we know how long it is in reality. Okay, and let's see what is next. The next one, is this triangle right triangle? So you always have to test if you're not sure. So leg, you can't assume it. You have to do leg squared plus leg squared equals hypotenuse squared, right? We're going to run this test on it. The legs have to be the lesser of the two. So the question really is this a hypotenuse or not? That's the question. Is 85 the hypotenuse because the greatest one? So we're going to do 13 and 84. So 13 squared plus 84 squared equals h squared. Well, we can even test it. Does that equal 85 squared? Right, that's our question. And then we're going to do 13, 84, and 85. We can do all these out. We'll do 13 squared, 84 squared, 85 squared, and 13. I'm going to actually add them together, so 13 squared and 84 squared. So you'll notice just quickly in my calculator, I did get that 85 squared does equal 13 squared plus 84 squared. They're both equal to 7,225. But I'm just going to show all my work for this. So 13 squared is 169. And then plus 7056 equals 7225. Was it 7225? Yep. And then we just have 7225 equals 7225, which is true. So the answer is yes, right triangle. All right, this next one, 16, 48, and 50. We want to know, is this the hypotenuse or not? It has to be it can only be a hypotenuse if it's across from a right angle. It can only be across from a right angle if it follows the Pythagorean theorem. So 16 squared plus 48 squared, does that equal 50 squared? Okay, 16 and 48. Hold on, let me get rid of some of these. Okay, 16 squared, 48 squared, 16 squared plus, 48 squared, and then 50 squared. You'll notice right away, I could have just done these last two steps. They are not equal, 2560 and 2500, but I just want to write out all my work. So 256 plus 2304. That equals 2500. Yep. And so 25, what do we get? 2560 does not equal 2500. So the answer is no, not a right triangle. And that's it for that one. All right. Classify the triangle whose side lengths are 6, 11, and 14. So remember, in this one, if we'll just copy this over. So here's our information. It's a right triangle if legs squared plus legs squared is equal to h squared. If h squared is greater than the sum of the legs squared, it's going to be obtuse, and if h squared is lesser, it'll be acute. So let's test to see how 14, remember we're going to go with 14 as the hypotenuse. So if this were to be a true problem, this would be a leg, that would be a leg, and that would be a hypotenuse. For this one, you have a leg, leg, and hypotenuse. Hypotenuse always have to be the greatest ones. So we're going to say 14 squared is equal to 11 squared plus 6 squared. It doesn't matter the order that those go in. So I have 121 and 36 and 196. Let's see, 14 squared, 196. So 196 equals, and here we have 157, right? 11 squared and 6 squared. 157, yep. So in this case, we do not have that they are equal. So it's not a right triangle, but 196 is greater than 157, which means that hypotenuse squared was greater than leg squared plus leg squared, which means that, here, let me go boom, boom, boom. Let's change this over to purple. Okay, so 196 does not equal 157. 196 is greater than 157. Therefore, h squared is greater than the sum of leg squared, making this an obtuse triangle. Think about it. The hypotenuse is greater, making the angle wider. Okay, and we are done with that one. All right, so we're going to do leg, leg, and hypotenuse for this. So 9 squared equals 7 squared plus 8 squared. So 81 equals, I already know this is not going to be that good. All right, so we have 81 is equal to 7 and 8. So that's 113. Let me just check my work. 113. Yes, so 113. So that's not true. 81 is lesser than 113, making the hypotenuse squared lesser than leg squared plus leg squared, making this an acute triangle. All right, let's take a look. Oh, looks like we're done. So we'll do some more of this in class. All right, we probably won't do this worksheet. We'll probably just do these questions. So I'll have that worksheet done for you. All right, good luck on this and the IXLs.